Welcome. My name is Joe Darcy. I work in Oracle's Java Platform group, and I'll be talking today about paths to support additional numeric types on the Java platform. On the last slide of the presentation, there will be a URL for a website where I'll be posting the slides later this afternoon. We'll be saving questions till the end of the talk. If there's not enough time for questions, feel free to catch me afterward or later on at the conference. So JavaOne, there tends to be two kinds of material in talks. One is talks that focus on features that have already been shipped and ready to use. Heard some of those at the keynote this morning, and I'm sure you'll be hearing those at the other sessions at the conference. Other sessions focus more on features that are in development and that may or may not ship in the future. And I encourage you to go to those talks at the conference as well. This talk today is firmly in the latter category. I'm mostly going to be talking about features that are in development and may or may not ship in the future. And if they do ship, will likely ship in a somewhat different form than what I'm talking about today, given future refinements and feedback. So a quick outline of what we'll be discussing after some motivation. We'll have a discussion about what is a type and what is a number, so we can better understand what numeric types are exactly. And then ways we could go about supporting numeric types on the platform. In particular, I'll talk about type classes and operator overloading as new features we're looking into. We've already put float16 into the platform as an incubating type in the vector API, so I'll talk about some experiences and lessons we've learned from doing that. And at the end, have some thoughts about curly modeling semantics, design considerations, including the design of the numerics of the new types we're working on, and then a little summary and Q of A. So why do we want to have more numeric types in the platform? Numeric types are very useful in different application areas. They're useful for traditional scientific and engineering computation. They're useful in an education setting and paving the on-ramp to bring the next generation of Java developers on board. And they're also useful in machine learning and AI. Machine learning and AI tends to benefit from smaller types than we typically have on the platform today. So platform support for numeric types involves a number of different aspects. One is deciding what additional kinds of types to include in the platform itself. And then if they are added, what aspects of the platform are used to support them? Are there new language features to support the types? Are there new virtual machine features? Are there core library features? And what combination of these three areas is necessary or best to support them? Besides adding new numeric types to the JDK, we also want to allow third-party developers, yourselves and other members of the community, develop and use their own numeric types for your own applications. So that's the exercise, trying to see what allocation of responsibility in different areas would be best. So given that this talk is in that latter category about things that are still being worked on, this is Oracle's safe harbor slide to give the appropriate warnings about how reliable it is, the things I'll be saying. And to emphasize at different points in the talk that the material is subject to change, I'll use these little photos of local Bay Area safe harbors as a reminder. So for some starting context, the reason we're working on numeric types now is because Project Valhalla is becoming closer to getting integrated into the platform, and we'll say a little bit more about that later. In particular, the valued classes feature from Project Valhalla that has a JEP, Java Enhancement Proposal, that's underway at the moment. Type classes is another language feature being looked at Valhalla to support numeric types. And by using the numeric types now, we hope to give feedback to the Valhalla project and collaborate with them to get a good result. So moving on to what is a type and what is a number. What is a type? This is a rich and complicated topic in computer science. One of the current reference textbooks on this is Benjamin Pierce's Types in Programming Languages. There are older definitions of types too. One of those is given in Wikipedia. That's the one we'll be using for our discussion today. So in this older notion of types, it focuses on a type has a set of values and a defined set of operations over those values. And of course, there's a lot more detail too. So in the Java platform, there's a historic divide between two fundamentally different kinds of types. There are the reference types, which we can declare and are included in the platform. So a sample reference type would be JavaOne string. The set of possible values for string would be the sequences of characters or code points if you're more Unicode savvy. And these values can be represented as string literals. For the allowable operations on string, we have the built-in string concatenation. And we also have all the static and instance methods on the JavaOne string class. And naturally, there's numerous other APIs everywhere in the Java ecosystem that either take strings or return them as a result. Strings, like other reference classes, have identity, and when you have an array of strings, you get an array of references. So you have to do pointer chasing for arrays. And on the other hand, we have primitive types. There are a fixed set of these built into the platform, in particular, say, int. The values for the int type are a particular subset of the mathematical integers. So we know these from min value to max value, so minus 2 to the 31 to 2 to the 31 minus 1. These can be represented by literals in the language. For the operations on the primitive int type, we have all the usual familiar arithmetic operations, comparisons, and so forth. Unlike reference values, primitive values do not have identity. They only have their value. So you can't, say, have a lock on the int value 3. Unlike for reference types, primitive arrays are dense. You don't have to do pointer chasing. And as constants, you can use arrays and annotations and other locations where you needed constants. So clearly, there are advantages to types on both sides of this divide. We would like to have things like user-declarable types for numeric types. However, these primitive types have a lot of performance and usability benefits in terms of operators. So why not have both? So this is one of the goals of Project Valhalla. One of the tagline is codes like a class, works like an int, to bridge the divide between reference types and primitive types and give us the best of both worlds. You'll probably hear more about Project Valhalla later this conference, such as in Brian Getz's keynote on Wednesday. And he's also spoken about this over the years. One recent talk would be at the Java Virtual Machine Language Summit from last summer. So with a little summary of types, what about numbers? Well, like types, numbers are a rich and complicated topic. Mathematicians have literally had thousands of years to come up with different kinds of numbers. So the sort of numbers I encountered in my math education before college were things like various kinds of integers, as well as fractions, rational numbers, real numbers, and then once we got the electricity chapters in physics, the complex numbers and the like. And there are many other kinds of numbers used in mathematics and computation. This is in no ways a exhaustive list. And these different mathematical types have different algebraic structures, which we'll touch on briefly later. So to get a better understanding of how numbers are structured and how they relate to things we might be more familiar with, I think it'd be helpful to have a short digression about how collections and abstract algebra might have some relationship to each other. So we're Java developers here at a conference, and let's say there was another conference attendee who was an algebraist, the sort of mathematician who worked on thinking about numbers and how they're structured. We might want to, and we wanted to talk about the sort of tools we use in to get our work done. So we might talk about collections as Java developers. So let's say we wanted to give someone a brief overview of what the Java collections framework look like. So let's say, well, we have some basic interfaces. There's a root interface collection, then we have lists and sets. There's actually a super interface of that iterable that lets collections work with the for each loop in the language. Comes out along the way. Besides the interfaces, we have abstract classes to help with implementations. There are more specialized interfaces for other functionality. For example, back in JDK 21, the sequence collections were added. These have a reversed operation and a defined encounter order. We have marker interfaces to indicate certain implementation properties like random access. That's very helpful to know. Some commonly used concrete classes would be things like ArrayList and HashSet. There are also concrete classes that implement the more specialized interfaces, TreeSet and LinkedHashSet. These are all generified. That's been done for a long time. And these are the collections in the JDK. There are multiple third-party implementations and extensions to these collection frameworks as well. So given this sort of a simple a picture of the collections framework, as someone who doesn't work in collections, do you have any questions about that? So if you were someone who wasn't already familiar with collections and worked on them for years, this might look very intimidating. So this is very familiar to us. We've worked with it a long time. But perhaps a way to approach this, to help explain it to someone who didn't have all this background and wasn't familiar with the approximately 30-year history of the collections framework, would be to take a different approach. So let's say if you wanted to have, say, 2 collection classes that would give you, a good starting point for how to use the framework as a whole, I'd recommend you start with things like ArrayList and HashMap. These are very useful, and each of these classes has a lot of extra properties that a collections framework might have. For example, ArrayList has that random access marker interfaces we mentioned. So that's a good way to get started. Now let's take a look about numbers. So as an algebraicist, numbers are very interesting. One of the great things about numbers is there's so many different kinds of them. A lot of people see, integers, rational numbers, reals, and complex when they're getting started, like in high school, but that's just the beginning. In fact, there are things called algebraic numbers that are between irrational numbers and real numbers. So algebraic numbers are the set of numbers you get by taking a polynomial and constraining it to only have integer coefficients. The algebraic numbers are the solutions to those kinds of polynomials. So things like the square root of 2 is an algebraic number, but things like pi and e are not. Those are transcendental numbers. So back in the 19th century, mathematicians had all kinds of extensions to complex numbers, like quaternions, but that was just the beginning. They have all these whole hypercomplex number family. Also in the 19th century, it was the first rigorous formalization of real numbers. We didn't really have a good understanding how real numbers work formally until relatively recently. But once we have real numbers, then you want to extend them. So you can add infinity to the real numbers in at least 2 different ways for the extended real numbers. But mathematics didn't stop in the 19th century. In the 20th century, there was the development of non-standard analysis. So real numbers weren't enough. Mathematicians developed super real numbers, hyper real numbers, culminating with surreal numbers. Surreal numbers were so inspiring that Donald Knuth wrote a novella about them. And the quote for that was, it shows how a lone couple turned on to pure mathematics and found total happiness. It's pretty spicy for a math book. But we're just getting started. Numbers are just the beginning. You want to care about what the sort of structures they have. So there are groups, rings, and fields. Those are very, very common. But again, that's just the beginning. We can make very fine distinctions between different kinds of groups, like abelian groups and commutative rings, all these great properties. And we can go on the smaller end too. There's something that looks really simple like a monoid. That's just an add operation and identity. But even that's kind of complicated. We can tease out very fine distinctions between things like there. But there's even more we can do. So we can take all these kinds of numbers we have, all these field elements and rings, and we can build more number-like things out of them. So we can take a field and we can make a vector space out of it. That's like matrices, linear algebra, that sort of thing. And polynomials themselves form a ring. Now, after having gone through an explanation like this, algebraicists might realize, well, now I've done the same thing with numbers that Java developer did with collections. This is a very imposing, intimidating summary with a lot of new terminology about things that might not be familiar. So another way to start thinking about numbers, like, okay, if there's only 2 kinds of numbers you want to focus on, you could think about integers and real numbers. Integers are a ring, real numbers are a field, and each of the integers and real numbers as rings and field have lots of other extra properties. So these are a good starting point. They have lots of special things. And one thing that integers and real numbers have in common with many other kinds of numbers is that you can add them, subtract them, multiply them, and divide them. So what are some of these commonalities between abstract algebra numbers and collections that we're more used to? Both areas have lots of details on a long history. There's lots of terminology specific to the field that might be unfamiliar. And fundamentally, they both involve abstraction. They both involve finding a small piece of commonality, separating that out, and then figuring out more ways to do that. We do that in Java as well. For example, back in JDK 7, there was the auto-closable interface that was added, which just has a single close method. So why we do that? Well, that allowed us to use the try with resources statement in a principled way, even though it was a very small interface. And in both cases, for like collections and these numbers, we can make productive use of the systems without knowing all the terminology and certainly all the implementation. For example, a formal construction of real numbers is quite non-trivial, and mathematicians took a while to get it right. But you can certainly use go through calculus classes and without knowing that kind of background and understand it perfectly well. So for numeric types in Java, we will not be trying to replicate all the richness of the mathematical structures, but we're going to be informed by that richness to try to make sure we can capture as much of it as makes sense. So I think that leaves us in a situation like this, where there's multiple considerations we want to keep in mind when working on Java numerics. We want to take into consideration the platform's current and future language features, the actual mathematics behind it, and separate from the mathematics, the computational properties. This is one of the areas where floating point comes in mind, which has both mathematical and computational aspect to it. So we're not trying to maximize the utility on any one axis, but we're trying to find solutions that satisfy on these multiple considerations. As James Gosling said many years ago in the field of Java, Java is not an academic language. It's to get various jobs done. And different numeric types are integral in getting different sorts of jobs done. So for the numeric types we have in the platform, as of today in JDK 26, we have those primitive types as well as BigInteger and BigDecimal. And what does being one of those primitive types get you? Once again, we have operators, literals, constant folding in the compiler. We know it works on every virtual machine. And it's also available for things like auto-vectorization in Hotspot and other virtual machines. And we get those dense arrays. So these are some of the sorts of properties we want to make sure are available for future numerical types in the platform. So what are some of the numerical types we'd want to have available for different kinds of jobs? So if you're doing traditional scientific and engineering computations, you would want types like complex and imaginary numbers and vectors and matrices. There's a group called Java Grande from years ago that had that sort of interest and made that exact recommendation. You might also want higher precision floating point types, something like quad. If you're interacting with databases or doing monetary calculations, you might want decimal types as well. In a machine learning context, it's more helpful to have a larger number of smaller numbers, smaller values, and there's multiple new formats being used in that space. I mentioned the float 16 format. There's a different 16-bit format called bfloat16, and there's even a 19-bit format which has the exponent size of one of the 16-bit formats and the significant size of the other. So it's kind of a hybrid format of sorts. The IEEE has a current project going to look into 8-bit floating point types in the machine learning space. And when I last looked at the recent draft, they had at least a dozen of them defined. So there's a lot of work going on in this area. There are many other sort of types you might want to have as well. Unsigned integers, classic, rational numbers. If you used Lisp or other programming languages that have a numerical tower, entries from there would be common. But there are many niche applications too that we want people to be able to write types to support. I mentioned earlier hypercomplex numbers. A particular one, quaternions, comes to mind. These are useful in some sorts of 3D graphics computations to handle rotations, as an example. So over on our branch in the Valhalla repo, we have various prototypes available already. We have some of those 16-bit floating point floater types, unsigned ints, exact ints, things that throw an exception if you overflow. We have some kind of textbook versions of complex 2 different ways. These would not be suitable for production use, as well as polynomials. And we have more prototypes planned, again, for decimal, rational, and different sizes of unsigned ints. So how can we get support for all these numeric types on the Java platform? One way to do it would be to try to support these new numeric types in the same way we've supported float and double over the years. So we could take a thought experiment about what that might involve. So we're going to look at where float and double are currently specified today and see what would have to be added to support types like float 16 or maybe decimal 128. So abstractly, what do we need to support a numeric type? We need to create the values from strings by converting from other values or from binary data. We have to operate on the values. And finally, we have to do textual output. So the specifications cover all these different areas. So these specifications range over the Java language specification, the JLS, the virtual machine specification, as well as various parts of the class libraries, both to use the values directly in the class libraries as well as to reflect over them. There's also specification work needed in J&I and FFM, as well as things like serialization. In the JLS, there are many sections needed to be updated that discuss, say, literals and conversions, lots of updates there. There's also additional sections on conversions. There's a table in the JLS that goes quadratically with the number of primitive types to say what can convert to what, and more updates needed for expressions and operations and operators. So what is the effect of all these specification requirements from the Java virtual machine, from the Java language specification? Those specifications allow Java-C to know how to compile an expression like A plus B based on the types of the A and B expressions. So after any necessary conversions, the options for Java-C are have a compilation error. So failure is an option here. Another option is to pick which of the 4 virtual machine instructions implement a differently typed add. If it's a double add, an int add, or a floater long. Another option is string concatenation. Like you can say string plus something else. And in this case, there's no VM instruction to use. So Java-C has to admit some instruction sequence without semantics. Historically, that's been called as string buffer or string builder, but more recently, actually for quite some time now, Java-C has used a different approach that relies on invoke dynamic. So this different approach is more amenable to the virtual machine, and the virtual machine finds this easier to optimize. The JLS isn't the only part that needs to be updated. We have to have a large number of updates to the virtual machine specification as well, data types, class file format, constant pools. So there are many things that need to be updated besides just the set of instructions. So we got some more of those here. Even the verification needs some small updates to handle new types. I will discuss the exact instructions in a little bit. The main point is many updates throughout the specification. This is summarizing just some of the class file structures that need to be updated to support a new primitive type. So these are the actual double related instructions we have in the instruction set. Comparison, arithmetic, there's multiple instructions for conversions to other primitive types, and then loads and stores. So the JVM instruction set is a byte code, so up to 256 possible instructions since it's a byte. So how many byte codes do we have to work with for possible future expansions? About 200 of the instructions are already allocated. So we have approximately 50 to work with. The problem is, if we do things as we do with float and double, each of those would require 20 instructions. So there's a very limited headroom to add additional types. Now there's plenty of tricks we could play if we wanted to build out support like this, but the main point is whatever budget we have for bytecode support is much, much less than the number of possible numeric types we might add not only to the JDK, but to the broader community. So we'll need to come up with something else. But that's not even all the support. There's reflective support that's needed. So primitive support throughout the platform is very extensive, and it is very widespread. So we would like to have some other way to do it. We would rather have an approach where we can update the language specification, the virtual machine specification, and the libraries once-ish, and unlock the ability to add more numeric types both in the platform itself and for third parties. So that's what we're going to do. And that's what we're looking into doing with Project Valhalla. One of the inspirations for the approach Project Valhalla is taking was Guy Steele's growing language keynote back in the late 90s at the UPSLA conference. If you haven't seen Guy's talk before, I do recommend reviewing it. There is a transcript of the talk, but I also recommend watching the video as the best example of programming language performance art that I'm aware of. So one of the quotes from Guy in his keynote was this: I might say yes to adding each of these kinds of numbers to the Java platform. He had his own long list of possible numeric types of interest, but I must say no to all of them. To add them all to the Java programming language would just be too much. And instead, Guy recommended making the Java language extensible so that it could support numeric types. The features he thought were necessary to get that extensibility were generics. So we added those back in JDK 5. Lightweight classes or value classes, that's coming now with Valhalla and JEP 401. And finally, operator overloading. So one mechanism we're looking to enable operator overloading is called type classes. This is a language feature from our functional programming language friends, initially developed for Haskell. And this provides a opt-in way to map an operator to a method on a class. And this achieves the goal of making primitives library defined and allows different primitive types to interoperate. And again, the details of this are subject to change as we work on the feature. So we've talked earlier about what numerical type support might look like. So again, a couple broad areas: literals, conversions between types, operators, and constant folding. So for type classes, we're initially looking at only supporting conversions between types and operators. So those other features, literals and constant folding, would be left to future work. Doing something like literals, there's various challenges to that. And one of the reasons is it's involving a very tight loop inside the compiler. So if we just had operators and conversions, I think the glass would be at least 80% full. So that's still pretty good if you're thirsty to quench your thirst. So I think that would still add a lot of utility to the platform. So when we talk about overloading operators, how many operators are we talking about? There are a lot of operators in Java. You go through the JLS, they're kind of grouped based on their syntactic properties. So increment, decrement, there's a number of unary operators, multiplicative, additive, and so forth. We have relational operators for comparison, equity, shifting, and bitwise and logical operators, and then a whole suite of assignment operators. So for the purposes of the numeric types, we don't want to allow these to be overloaded individually. We want to bundle related groups of operations together. So our current thinking is we'd have an interface, something like numerical, that would mean you could use the arithmetic operators, add, subtract, multiply, divide, and so forth. There'd be a separate interface to say orderable. You could use the comparison operators. Ordered numerical if you use both. The reason these all aren't combined in one, the arithmetic and ordered operators, is there are some kinds of numbers that aren't ordered. Mathematically, for instance, the complex numbers are not ordered. They're not an ordered field. There'd also be a separate interface for an integer-like type, integral, that would allow you to use all the arithmetic and comparison operators, but you'd get access to all the integer-related operators as well. And finally, a standard floating point sort of interface that would include all the ordered numerical ones, as well as other methods that were appropriate to an IEEE style floating point type. So what would this kind of interface look like? It'd be pretty straightforward. There'd be an add method that would be documented to cover the plus operation, a subtract method that would map to minus, and so forth. This is what the code using the witness would look like in, say, the unsigned integer class. There would be a object implementing the integral interface. So we'd have the implementations of the methods there, say the add method of the interface, and the expected implementation of this, it would call the static add method of the unsigned int type. So it would kind of do the redirection for you. And there'd be some other syntax, subject to change, as a language feature that would register the witness with the compiler so the compiler knew where to look when it saw a operator that was acting on an unsigned int. So that's what, so the to-be-written language rules would tell Java-C where to look for witnesses and what the mapping of operator to method on the witness would be. And the intention here would be to use code generation idioms that would be easy for Hotspot to digest, like what was done for the string concatenation in more recent Java releases. So this is an existing incubating type for float 16. So this is what the patch to upgrade it to use operators would look like. First, we have to change it from a class to a value class. It's a new category of class that Valhalla is working on. And then we'd have the witness object and the registration of the witness itself. In terms of the use of the code, it would look something like this. You'd have your float 16 values, A and B. You could sum them up. If we use java.p to decompile them, we would see there'd be this LDC to get the witness object. And then after we loaded the arguments, we'd call the add method from the numerical interface on that witness object. And if we were doing this sort of feature pre-invoke dynamic, we'd use a different idiom, but now we can use this idiom that the VM likes to consume. So what kind of witnesses do we have? It's not too surprising for the prototype. So the floating point types have the floating point witness. The integer types like unsigned int and exact int have the integral witness. The complex numbers have a numerical witness, again, because they're not ordered. And we also have that polynomial type that only has numerical, since it's not ordered either. For the types that we have planned, things like the decimal types would either be floating point or numerical, and likewise rational would be numeric, and so forth. So there are various design constraints we're working with for type classes, at least in this first iteration. One is that we're assuming there's a homogeneous typing, meaning you would have foo, op, foo, yields a foo. And that this would be enough, at least enough to get started for the first few iterations. So we're not trying to support mixed type operations, where you could have different types for the two operands. So there are cases where it's known that this homogeneity is not ideal, say for complex arithmetic. You'd want to say, ideally if you multiplied two imaginary values, you get a double back versus just a complex. Also for matrices, there's a semantic distinction between a 1-by-1 vector or 1-by-1 matrix and a scalar. So if you couldn't say multiply a scalar by a matrix and boxed it into a vector, that's a little bit breaking a system, but we could probably make that work. But ideally would like the type system to handle that. So that is background. We'll look at some of the experience we've had so far with float 16 and some paths that points to going in the future. We initially added float 16 in the vector incubator area back in JDK 24. As of JDK 25, it has intrinsic support on multiple platforms, thanks especially to our friends in the OpenJ community collaborating on this, in particular Intel, who's on the vanguard of adding support like this. So if you use a recent enough JDK and your laptop is new enough, you might already be having float 16 intrinsified support when you run your Java programs. So, and we can take a quick demo to look at what float 16 with operators on that Valhalla branch we have going. Just let me switch here. So we're going to, let's get the focus. All right, so we're going to start up JShell. Based on that JDK build of the branch. Okay, good. Focus. Okay. So we want to import the float 16 type. So now we can get some float 16 values. And there are multiple factories we can use. Okay. So we can convert from strings as well as from integer values as expected. So there is a static divide method on float 16. And we get back a low precision result. And we can see if we use the divide operator, we get back the same result. And we can see that float 16 has less precision than float. If we convert the values to float instead of float 16, we see we get a much longer fraction back. Okay. What did it take to implement float 16 is a few thousand lines of code and about another 1,000 lines of regression tests for the way we implemented it. There are many things we did not implement. We did not implement format-specific sine, cosine, or tangent. Of course, we don't have those for float either, unlike in, say, the C math library. There were many things about implementing float 16 that went as expected, that were pretty straightforward to use. So using a little bit of numerical analysis knowledge, there is the 2p plus 2 property. So let's say you have a narrow floating point format you want to implement and a wider one. Can you just convert from the narrow one to the wider one, do the arithmetic in the wider one, and round back? So have the wider format do most of the heavy lifting for you. And the answer is sometimes yes. And that holds true when the wider format has twice the precision plus a little bit more. You get two more digits. By design, the different formats in the IEEE standard have this property, so we can use the float format to implement exactly the arithmetic of float 16. So the implementation of the float 16 add operation just takes both operands, converts them to float, which is pretty straightforward, does the arithmetic in float, which is built into the platform, and then converts back to float 16. And that gets exactly the same result as you would get doing the float 16 work directly. So 2p plus 2 is great when you can use it, but there are times you can't use it. One of the times you can't use it is with the fuse multiply add operation. That's a times b plus c with only a single rounding error. So this is the code from float 16 that implements FMA. So this is the spec, not too bad. And the implementation's only 2 lines. So the rest of this is comments explaining why those 2 lines are actually correct. So sometimes that's how your numerical code works. You get a couple pounds of comments for an ounce of code. So there would have been a way to implement float 16 with less thinking about rounding errors and the like. And that would be if we first implemented conversions from float 16 to big decimal, and then we could do everything exactly in big decimal and round back. That would have been another way to do it. One of the reasons we did the work on the other slide the way we did is because we hadn't taken the steps to make the conversions first. But if you were implementing your own type, converting some wider type to do the computations for you and then converting back would be a good way to get started, assuming you had that wider type available. Another thing that took some work for float 16 was getting the base conversions work between a binary and decimal such that they obeyed the usual shortest string properly. So we saw when we divided 1 by 3 as a float 16, we didn't get that many digits. We only got as many digits as we needed to reconstitute the value. So we weren't, in particular, giving a misleadingly long string back to imply that there was more precision in the format than you actually had. So in particular, if you wanted to implement something like that 19-bit format that we saw earlier, some of the basic operations would be straightforward, but if you wanted to support something like FMA, that would require more work and more thinking, and that correctly on base conversion could be tricky. So some infrastructure we're considering to allow other parties to write new binary formats of other precisions would be something like a big binary class in the platform that wouldn't be aimed at end users, but at library developers. So this class could do things like have a math context object similar to big decimal, but instead of just rounding the precision of the results, also round the exponent range. Because some of the tricky rounding cases involved, say, the subnormal range where you have fewer digits available. So what are some current thoughts on modeling numerics based on what we've done so far and some things we're looking at in the future? So you might be thinking, oh, this is a talk about Java numerics. What about JavaLang number? Yes, what about it? So unfortunately, there's very little numeric about JavaLang number. It just operationally means you can be converted to primitive type. You can't really do anything with a JavaLang number as a number. There are no methods other than conversion methods defined. So JavaLang number is not a solid foundation for future work. So we have to kind of look elsewhere. So while the current set of interfaces we have to model the interfaces is pretty solid, there are many design points to consider, even with what we have. So for instance, let's take negation. So that's currently in the numerical interface. So how should something like negation be defined for an unsigned type, like an unsigned integer? Well, in some cases, the JLS defines negation as subtraction from 0. We could certainly do that. If negation is defined for integers, should we define it that way, or should we just have it unconditionally throw an exception because it's kind of a programming error, because it's unsigned after all? We could do something like add an additional interface like unsigned integral instead of integral that didn't have the negate interface, and then we could avoid having to come up with a definition for it because the method wouldn't exist. So this is a small illustration of a common design tension between lumpers and splitters. So this has been around at least as long as people have been arguing about how many species a set of animals takes up. So the splitter solution would be to use unsigned integral to avoid having to find the negate method, and the lumper solution would just be come up with some policy for negate on unsigned. Neither one is necessarily right or wrong. There's a tension. Currently, we're performing a more lumpier approach. There are also design considerations, including numeric considerations for a type like complex. So complex numbers are an interesting case. We have some bug open to look at them. So they're useful in engineering calculations. They're also actually very fundamental to mathematics. So if you want to talk about the roots of polynomials with real coefficients, you need to talk about complex numbers, because those roots are complex numbers. So complex numbers are tied into the fundamental theorem of algebra. So while complex numbers are commonly used as an introductory example for abstract data types, kind of in a CS 101 sense, if you want a more advanced version of complex for production use, there are many other considerations to take into account. So again, if you're looking at a kind of a CS 101 kind of guided discussion about how to think about complex, there's a good example of this in Josh Bloch's Effective Java book. Well, how do you want to model the complex number? Is it a class? Or now, more recently, is it a record? Or after Valhalla, is it a value class? You know, how do you declare it? Which methods are final versus non-final? Access levels, what methods are static versus instant methods, and so forth. Another basic modeling consideration, do you use real and imaginary components for the complex, or do you have a magnitude and a phase angle? Both can be helpful in different circumstances. So for operator overloading, while complex numbers mathematically aren't ordered, do you want to impose an order anyway? So you could sort your complex numbers if it doesn't have an ordering, you can't sort it. A common operation for complex that we don't see in real or integer computations is conjugation. That's where you're just negating the imaginary component, but not the real one. So if you look at any textbook that discusses complex numbers, there are complex conjugation symbols everywhere. They're talking about complex. So it's really fundamental for complex. So do we want to add that sort of operator, say a tilde operator for complex conjugation? Well, it kind of depends what your priorities are. If your priority is making sure we have a really great complex type, sure, because it's fundamental complex. But if you're taking a broader perspective, it's like, well, it's just one kind of number. Do we really want to define a new kind of interface in JavaLang just to support complex? Well, in the end, maybe not. So that's some of the considerations to keep in mind. And complex numbers would bring out all the other support options we've been talking about, like literals or constant folding. We would also want to see how complex in a Java environment would compare to complex as it is in other language environments like C, C# or Swift. But there are numerical design implementations as well. So infinities and nands, those are complicated for real numbers. They're even more complicated for complex numbers. Another issue is, do we want a single complex number, or want complex as a generic type where we could work over different precisions? Maybe you want complex over float or double or something extensible thing. There's some trickiness in defining the complex math library in terms of things called branch cuts and complex analysis. And there's lots of error bounds, even for the basic arithmetic operations. So here's one quick example. Let's say we want to look at the specification for complex multiply. So the textbook formula, you give an a plus bi and c plus di, and you can see what the product is. So each of the real and imaginary components is computed with just 3 floating point operations, to multiply and add or subtract. So what's the problem? Well, even something this simple, there are some numerical dragons there. You get the possibility for cancellation and overflow. That's even without any of the other special case handling. Should the specification for complex multiply give any bounds on the accuracy of the results? Sometimes there are formulas you could use where one of the real and imaginary components would be accurate, but the other one could be basically totally wrong. Is that okay? Sometimes yes, sometimes no. If you flip the order of the operands to multiply, should you get more or less the same result? There are formulas where you do and some that you don't. The ones where you do get the same result each way cost more to compute. So is that worthwhile? Possibly. So like, what are some of the, if you wanted a commutative, accurate version of complex multiply, this is what it would look like. This is one way you could do it. So this method here computes the AD, BC sort of thing as we saw before. But it does it in a clever and seemingly redundant way. So first it multiplies a times d together, just normally. Then it uses a fuse multiply add where it multiplies a and d together again, but now it subtracts the first product of a and d. So what's it doing here? So mathematically that should be 0, right? Because it's AD minus AD. But this is floating point. So what this is doing, it's recovering what was rounded off from the first product of a times d. So we've recovered all the bits of the product of AD using this technique. So why do we want to do that? Well, if we have the two products, let's say the two products are close to each other in magnitude. When we subtract them from each other, most of the bits get canceled out. So instead of having a result that has this many bits of information, now we'd have a result that has this many bits. We have many fewer bits than the precision of our floating point result. By keeping the rounded off components around from the products, we can compute those and add that back into the final result and restore all full precision output. So this is great from a semantic point of view. However, rather than 3 floating point operations, it takes between 7 and 9, depending on how you count the FMAs. So is that worthwhile? In some contexts it would be, but sometimes you want to go full speed as well. So it depends on what your goals are. However, for the Java platform, I would say our users should have few occasions to have to understand the details of error behavior of complex operations or other things. But we want to provide accurate operations and certainly provide the tools that library writers could make accurate tools for their users as well. So in summary, there's many numeric types of practical interest. The platform support is needed to get good integration, particularly for operators. Project Valhalla features are going to be useful for numerical prototypes, and there's a lot more to do. One of the things we're going to work on next is interesting conversions between the existing prototype numerical types, and we expect to write more prototypes and to refine the ones we have today. So it's fun times ahead. And again, final safe harbor reminder. And now we might have time for maybe one question since we're almost at the end. So the question was about infinitesimals. Those are something that I've come across them in non-standard analysis. So they wouldn't be too relevant here. So that would be something like the surreal numbers would deal with infinitesimal values. The question was whether the types would be sealed or not. So currently the design, that these have to be value types, so those would be implicitly final. So you could use them as components, but so there'd have to be another thing for code reuse. So the question was whether the semantics would change based on the hardware architecture running on, or if the language spec or library specification would dictate the semantics. It would depend. The default answer would be it would be cross-platform, and you should have the same results defined everywhere. You could, in some cases, have, say, a library they gave license to have platform-specific results. So we do say in java.math to get better performance on the math libraries, but it's more of an exceptional case in the Java platform. So I think we're out of time now, so thank you for coming. And again, if you have other questions, catch me later.